take some tea and have a seat. I was thinking about some cool math the other day, and I want to talk about this idea of moving between worlds as a way of thinking about problem-solving strategies and a way of thinking about how to represent information in different kinds of data structures. But before we get to that, we gotta learn how to peel onions. We'll start with the so-called Peano definition of natural numbers, which says that any natural number either looks like 0 or it looks like the successor of another natural number. Successor is like the plus 1. So we're saying that any natural number, if it's not 0, then it could be written as 1 plus something else. I'm going to call natural numbers nat here as a shorthand. And let's try to see what different numbers would look like with this. So our usual 0 is going to look like 0. Our usual 1 is going to look like 1 plus 0, so S0. Our usual 2 is going to look like S of S0. So it's 1 plus 1. Okay, so you can imagine how every natural number can be written as this big onion of S, 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 and in the middle we have 0. Let's try to do some things with this. Let's try to figure out how to double any natural number. So I want to write a function double that takes a natural number and spits out another natural number, now doubled. Since our definition of a natural number is inductive, meaning that the definition is in terms of itself with this S-nat, let's try to follow this inductive structure. So we give double a natural number, and it looks at it, and there are two cases. Either we have 0, or we have S of another natural number. Let's consider each case separately. Double of 0 is going to be 0, because we want 2 times 0 to be 0. And double of a non-zero number is going to look like double of Sn. And that, let's figure out what that says. So this is like saying we're doing 2 times 1 plus n. If we expand out the brackets, that's like saying 2 times 1 plus 2 times n. And 2 times 1 is 2. So we're left with 2 plus 2 times n. Let's see if we could write this in terms of s's. So this 2 plus, we could write that as s of something. And that something here is going to be this 2 times n. And that's good news because 2 times n is exactly double n. So that means we could write this double Sn as s of double n. You can see that now we have a recursive structure where the double for a non-zero number is going to call itself again. Let's do an example to see how this works. So let's try doubling 2. So if we had double of 2, I'm going to write it like a tree. It's going to be double of s of 0. First, the double is going to look at the outer layer of the onion and go, oh, there's an s here. Let's expand it out. S double n. So it's going to do s, and then it's going to apply that to double of the rest of the number, which in this case is double of 1. You see how this part of the first tree became here. Okay, well, then the inside double is going to look at this inner onion and go, okay, we're still not to the center. And let's do the same thing again. So we have SS again, and we're going to double the rest of the onion. Well, double of 0 is just 0. So what we're left with is going to be SS, SS, 0. And if we expand out these SS, this is going to have 4 S's in total, which means that our answer is 4, like we expected. Okay, that's nice, and I think quite elegant. Look at how little work we had to do to make a double function from a very primitive definition. Well, let's try to do something fancier. Let's try to do powers of 2. So we want a function exp2 that takes a natural number and spits out a natural number. It returns 2 to the n, if n is the input. We'll do it case by case again, so that seems to be quite a natural thing to do with our piano definition. So we have exp2 of 0. 2 to the power of 0 is 1, so that's going to be s0. exp2 of non-zero number, well, that's like saying we have 2 to the power of 1 plus n, which if we expand out is the same as 2 times 2 to the power of n. And okay, that's quite neat. So this first 2 times part, that's the double function we just wrote. And this inside 2 to the n, that's actually exp2 of n. So again, we could do this recursive style. And if we write it out, say 2 to the power of 2 in a tree format, we're interested in exp2 of s of 0. The exp2 is going to look at the outer layer of the onion and say, oh, we're not to the center. And then replace that with a double, and then do exp2 on the rest of the onion. Okay, so it looks at the s, and instead it does double of exp2 of the rest of the thing. Now let's go one more time. So the next layer down is going to say we're still not to the center. And now for exp2 of 0, it's going to say, okay, now we're at the center of the onion, the center of the universe. We're going to take the 0 and make it a 1. So our final answer is double of 1. And we could expand this out using the definition of double, or just look at it and say, yeah, answer is 4, like we expected. At this point, we might be noticing a pattern, which is that our input, the tree of our input, has the same structure, the same number of layers as the tree of our output. And it always follows this idea of replacing s with something else. So here it's s with double. And replacing the 0 with something else. Here it's 0 with 1. If we go back to our double, we could see that double is going to take an s and replace it with ss. And it's going to take the 0 and replace it with 0, since double 0 is 0. So now we might think, okay, so this natural way of writing functions inductively on natural numbers for our piano numbers, it seems to all have the same pattern of replacing s's with something else, replacing zeros with something else. I wonder if we could abstract it. And this idea is capturing this same recursive structure. It's called a fold. So I'm going to write a function called fold n. And fold n is going to take 2 parameters. It's going to take what you replace 0 with, with Z, and Y you replace S with an S. And what it does to some natural number, say 2, what it's going to do is replace all the S's with little s and replace the 0 with the Z. Let's see how we could write a definition for fold n. Since fold n is a generalization of these kind of onion peeling functions, it itself is an onion peeling function. So we look at the case, oops, I should use little s. We look at the case when we give it 0, and it's going to look at it and go, okay, I replace it with Z. We look at the case when we input successor of something, and what it's going to do is replace that big S with the little s. And the little s is going to be applied to the rest of the onion, or rather the output of the rest of the onion, the fold of the rest of the onion. So it's going to be s of the same function, the fold n of z s n. I call it fold n for natural numbers if I didn't say that. Okay, well, now let's see how we could write double and exp2 as instances of fold n. So double is going to replace each s with ss. So the s term is going to become ss. And it's going to replace the z with a 0. So the z term is going to be 0. There we go. And then exp2, it's going to replace the 0 with a 1. So replace 0 with s0. And it's going to replace the s with a double. And there we go. I really love that. It's like who needs to repeat work? But now, whenever we have some onion peeling function in mind, we just need to think, okay, how would we write it as a fold? How do we replace the 0? How do we replace the s? And we're done. This is everything. Not only that, it really captures how these natural ways of writing functions all belong to the same family because they all look so similar. But that's natural numbers, and you could think of many more folds. A challenge is to figure out, how do you write a plus b as a fold? Or how do you write a plus b for natural numbers in general? But we'll think about that later. Nice. And instead, we'll move on to lists. Because I want to show you that fold is not only a natural number thing. It is an everything thing. Onion peeling functions for any kind of exotic onion could be captured. So there are many ways of writing lists. You could have lists where it's very fast to insert anything into anywhere in the list. Or a list where it's very easy to access any position of the list. Or a list where it's very easy to put things to the end. Or a list where it's very easy to sort things. We're going to do a simple list. And this is going to be called a cons list. So we're going to say that a cons list of type A is going to either look like the empty list, or it's going to look like something and then another list. And then it's called a cons. So here it's saying that we're going to put something in front of the rest of the list. And this A here is a type. So A could be int for a list of integers, or A could be nat for a list of natural numbers. A could be lists, actually. It could be lists of natural numbers. Then you'd have to have a list of lists of natural numbers. Or you have like a list of lists of lists. Okay, it goes on. And I'm going to use a shorthand. So for example, the list 2, 3, 4 is what that's saying is really 2 const onto the rest of the list, which is 3 const onto the rest of the list, which is 4 const onto the empty list. So kind of like the piano natural numbers, any cons list is this big onion that have conses as the outer layers and the empty list as the very heart. Let's try to find the sum of a list of integers. Okay, so how do we do that? Well, let's do the thing with natural numbers and peel the onion layer by layer. Look at the outer layer. Is it empty? If it is, you got nothing to add, so it's 0. If it's non-empty, it could be written in the form x cons x's, where x is an integer and x's is the remaining list of integers. Then what we want to do is take the first thing and add it on to the sum of the rest of the thing. Okay, that's it. And if we apply that to our list, favorite list now, 2, 3, 4, I'm going to write a list in tree form like this. So we could look at this as this list is 2 const onto the rest of the list, which is 3 const onto the rest of the list, which is 4 const onto the empty list. And I write it like a tree. Is actually, this is the expression tree of the cons list. It is exactly this expression, but in a more readable form. Okay, so our sum onion peeling function is going to look at the first layer and go, oh, it's a cons. Let's do x plus the sum of the rest of the list. Well, the x here is 2. So we're going to do 2 plus the sum of cons, 3 cons, 4 cons, empty. You can see that we've replaced the cons with a plus. So we could carry on this way and replace this cons with a plus. Replace the next cons with a plus. And what about the empty list? Well, it's going to be replaced with sum of the empty list, which is 0. Okay, so that's our answer. And it makes sense. The sum of the list 2, 3, 4 is 2 plus 3 plus 4 plus 0. Nice. And you can see that we're always replacing the conses with pluses. Now let's do another example, which is something functional programmers love. No, not examples, but like this thing we're doing. We're going to implement something called a map. A map is going to take a function f, and it's going to apply f to every single element of the list you give it to. So this is really useful. It's what you would usually do with a while or for loop in a normal programming language. And the idea is you go through each thing in the list, and then you do something to each element. You could double it, maybe. You could check if it's a valid input. You could check if it's a prime number. You could maybe just take a list of words and give you a list of first characters, or give you a list of words and give you the length of each word. It's very useful. Shows up all over the place. Well, let's try to write it. So map f of an empty list. You've got nothing to do, so you do nothing. Map f of a non-empty list. Well, we take the first thing in the list, we apply f to it, and then we put that to the front of applying f to the rest of the list, which is map f x's. you can see how this is gonna unpeel itself, this onion. It's gonna do fx1 and then cons down to fx2, cons down to fx3, cons down to etc. until we get to the very end when it conses onto an empty list. That's really nice. And if we apply that to a list, our favorite list. No, not 2, 3, 4 this time. Let's just do a quick one. x1 cons down to x2, which is then cons down to the empty list. What it's going to do is look at the first layer of the onion and say, okay, we're going to do fx cons down to the map of the rest of the list. Right. Well, and it's going to do the same thing next. It's going to say, okay, we're still not at the center of the onion. Do fx2 cons down to map f of the empty list, which is just the empty list. Nice. This is what we wanted. Okay. Now we're going to do fold on lists. Let's look at the pattern we have with sum and map. All we have is that each of these onion peeling functions is going to have an empty list case and a non-empty list case. And the non-empty list case is going to replace the cons with something. So maybe here, replace the cons with plus, or in map, replace the cons with cons. And it's going to also do something to the first thing in the list. So for sum, it does nothing. But in map, it applies f to the first thing. So in general, we're going to need our fold, our onion peeling, is going to allow us to combine the first element of the list somehow with the result, the output of the rest of the list, the fold of the rest of the list. Let's write that down. So we're going to have fold. I'm going to call it fold L for fold list. And it's going to take in two things. The thing you replace the empty list by, E, and the thing you replace cons by, which I'm going to call cons. And it's going to take a list, say our now second favorite list, x1 cons, x2 cons, empty. And it's going to replace all the conses with little English cons. And it's going to replace the empty list with E. So let's write that out. So fold L, E cons, empty list is going to be E. And fold L, E cons, non-empty list, x cons x's. It's going to do cons of x onto the fold of the rest of the list. So like the cons of x onto fold of the rest of the list. We're going to need a new line for that. We're going to do x cons fold L E cons of the rest of the list. So the back quotes I put here, that just means I'm thinking about this little cons as an operator, as a thing that takes in two arguments and spits out another argument. Okay. So fold L is again an onion peeling function, since it is the family. It could represent anything in the family of list onion peeling functions. Let's write out our earlier examples, map and what was the other one? Whatever the other one was, as folds. So map F is equal to fold L of, it's going to replace the empty list with the empty list. And this cons, it's going to apply F to the first thing in the list, and then cons it onto the rest of the list. But that's a bit complicated to write down, so I'm gonna give myself a cheat, not a cheat, just more lines of code, where cons of where x cons onto the result of the rest of the fold is gonna be equal to f x cons onto the result of the fold. Okay. Cool, right? This is like more concise than the map earlier, and it puts it into this family. Oh, the other one was sum, right? So sum, it's gonna take the empty list and replace it with a 0. Take the cons, replace it with a plus, and that's it. Now this gives us more ideas. We could write maybe product as fold L of 1 and times, and that's it. That's product. No more work. Easy. Instant solve. And I'll leave you with the challenge. How do we write this cat function as a fold? So cat is gonna take in two lists, and it's gonna spit out both of the lists concatenated together. So this is a bit like the plus question I gave earlier. Yeah, it's a fun thing to try. So that's peeling onions, and have a tea break. Next, we'll continue with reconstructing onions before we could finally use the onions to travel between worlds.